Okay. Now let's recall the following definition of the what we call cofactor. So A is a square matrix with entries Aij, n by n matrix A. The RS cofactor, the Rx minor matrix of A, denoted by MRS, is obtained from A by deleting the rth row and the S column. Okay, so if A is written out explicitly like this, A11, A12, A1S, A1N, A21, A22, A2S, A2N, AR1, AR2, ARS, ARN, AN1, AN2, ANS, ANN. Then we're deleting the rth row. That's here. Ooh. AR1, AR2. We're deleting the rth row. So that is here. Also deleting the S column. So that's here. And we should push everything what's left together to a matrix of size m by m minus 1 by m minus 1. Okay, so MRS is of size m minus 1 by m minus 1 matrix. Okay, and now let's see here. And we've seen in some examples that we can consider expanding along different rows. So let's formalize this for A. So say the ith row cofactor expansion is the following. Okay, you're looking at the ith row. So there's always a sign -1 to the I plus j. Aij, I is fixed. Determinant of Mij, where you let j run. Right, ith row, j goes from 1 to n. Okay. And similarly, you can define the expansion along the columns. The j's column cofactor expansion is, again, the similar expression, -1 raised to the power of I plus j, Aij determinant of Mij. Now j is fixed now because we are moving along the j's column, so let I run from 1 to n. Okay. So let's highlight this. If we're looking at the ith row expansion, I is fixed. I is fixed, J is running. If we are looking at the J's column expansion, J is fixed, I is running. Okay. Now it's an important but somewhat tedious to check fact that the i's row cofactor expansion is equal to the J's column cofactor expansion for any I and J. Okay, so what this means is that no matter which row you choose to work with or which column you choose to work with, this expression we have here and this expression or this expression will give you the same number. Therefore, it makes sense to associate that number to the matrix A. The determinant, that's the determinant of A is, for example, the first row expansion minus 1 plus J, A1J, determinant 1 M1J, and the point of this theorem is saying that this is equal to, also equal to the sum of, well, the expansion along any row for any I, and this is also equal to the expansion along any column for any J. Okay, we've seen how this worked in one example before. Let's see this in another example. Okay, a more complicated one. But in any case, before we proceed to example, what we're doing here is we define the quantity for the matrix A called the determinant. It's defined in terms of some expansion along a column or a row of the matrix A. So let's look at now some example. Let's consider this A. Let's take a 4x4 example. Minus 1, 1, minus 2, 1, 2. And we can calculate the determinant by the first row expansion. So first row expansion. Okay, and that is the following gadget. First of all, let's write out what we need. A11 determinant of M11 minus A12 determinant of M12 plus A13 determinant M13 minus A14 determinant M14. Okay, so this is what we need to compute. determinant of, we have 4 determinants to compute, right? Let's see. So we have, first of all, the M11. To find M11 is going to come from deleting the first row and the first column. So how do I do this nicely? Deleting the first row and the first column. What's left is this. So the determinant we're computing is the following. Okay. And so this we can then continue to follow the definition using the first row expansion. And that's going to give us this expression. Okay. Let's check before we proceed. Yes. Okay, so the first thing goes away because you multiply by 0. Second term is minus 2, minus 2. The third term is minus 2, 1. So this is 2 minus 2, that's 0. Are we sure? No, this is not 2, but it's 2. Because the first term is a 4. 4 minus 2, that's a 2. Okay. It's important to be careful. Now, for M12, what do we need? We need to delete the first row, second column. Oops, not that. First row, second column. What's left? Minus 1, 3, 2. 2, 1, minus 1, minus 2, 1, 2, which we then compute using the same recipe. 3, 2, 1, 2 plus negative 2 times 3, 2, 1, minus 1. Okay, looks correct to me. Then we proceed. Minus 1 times, what is this? 2 minus negative 1, so 3. Minus 2. 6 minus 2. Plus negative 2. Minus 3 minus 2. Okay. So that's minus 3. 6 minus 2, that's a 4. So 4, 2, that's negative 8. And here I have minus 5. Minus 2. So minus 5 times minus 2, so that's a plus 10. So negative 11 plus 10 is negative 1. Okay. Now, for M13, what do? We again delete the first row, third column. What's left is third column is gone now, so it's minus 1, 3, 2, 0, minus 1, 0, minus 2, 1, 2. Okay, and this we can then compute by the stem recipe. 3, 2, 1, 2. Yeah, plus negative 2, 3, 2, minus 1, 0. Okay. And the middle term goes away because it's a product of 0 and something else. The other terms look like these. So it's -1 times, well, this is -2. -2 times that's 0 minus 2, 0 minus -2, so +2. So what do we have? 2 minus 4, -2. Okay, so one more. Determinant of M14. So M14 is going to be, you're going to delete the first row, last column, or the fourth column. So that is -132 -132, 0 minus 1, 0, and 2 minus 1, 2, 1 minus 1. Okay, and you compute again, like that. -0 times something, +2 times something, like that. And the middle term goes away again. What's left is -1 times 1 +2 times, this is 0 minus -2, so +2. So 4 minus 1, that's 3. Okay, so now we've computed the 4 determinants we need. Let's reproduce the formula for the determinant. 2 plus A13 determinant M13 minus A14 determinant M14. Now we can plug everything in. A11 is 1, and M11 is 2, minus A12 is 2, M12 is -1, A13 is -1, M13 is -2, and finally A14 is a 1, M14 is 3. So now this is easy because this is 2 minus -2, so 2 plus 2 plus 2 minus 3, so it's 3. All right, finally. That took a while. Now let's, as far as example goes, let's look at the determinant again using expansion along a different column or a different row. And here we're going to try to do this. We're going to try to compute a determinant using the expansion along the second column here. And the reason for that is you see the second column has 2 0 entries. So this is, according to what I stated before, the determinant of A is also equal to the expansion along second column, which is A12. No, there's a sign here. -1 or minus A12 that A12 plus A22 that M22 minus A32 that M32 minus plus A42 that M42. Okay, and now this is a simpler computation because let's see, we need to go back to C here. A22 is 0. This is 0. So that entire term goes away. A42 is also 0. So that entire term goes away. So what I need is to compute the determinant of M12 and the determinant of M32. That's easier to do. And we'll just do it. Determinant M12, we've done it already, right? That's -1. It's -1. Now the determinant of M32 that we have to do. So we delete. So we end up getting 1 minus 1, 2, minus 1, 2, minus 1, and 1 minus 2, 2. Okay, and this we can compute by the basic recipe. 2 here, and minus -1 times minus 1, 2, minus 2, 2, plus 1 times minus 1, 2, 2 minus 1. Okay. Yes. Okay, so now we just compute. So it's 4 minus 2, so it's a 2 here, minus minus 1. There's -2 minus -4. So -2 plus 4, so that's a 2, plus this is 1 minus 4, -3. So this comes out to be 2 plus 2, that's 4, minus 3, that's 1. Okay. Okay, so very well. Now we're ready to proceed. We'll still have to know M12, sorry, A12. A12 is 2. So -2, -1, minus A32 is a -1. -1 times 1. So what is this? This is 2 plus 1, so 3. Okay, and you see that they are indeed equal. So for some reason that we do not want to discuss here, this the expansion along different rows and the different columns all give you the same number, and that number is called the determinant. Okay. All right. Now we're gonna proceed to study properties of determinants. Okay. So let's see. The first one, let's state this as a theorem, I guess. Theorem. Let's say you have two matrices, A and B, both of size n by n. Then you have the determinant. Well, first of all, you have A times B, which is also n by n. So you have its determinant. And the statement of the theorem is that determinant is determinant of A times determinant of B. Okay. Well, we're not actually going to prove this in general, but let's just check the 2 by 2 case. Okay. So let's suppose you have A being A, B, C, D, B being R, S, T, U. Then AB is AR plus BT plus BT, AS plus BU, CR plus DT, CS plus DU. Okay. And determinant of AB is then the following product: AR plus BT, CS plus DU minus, AS plus BU, CR plus DT. And what else can be done at this point except to expand ARCS plus ARDU plus BTCS plus BTDU minus a bunch of things: ASCR plus ASDT plus BUCR plus BU DT. Okay. So now we can see some cancellation. ARCS is the same as ASCR. Good. Let's see what else can be canceled. BTDU is the same as BUDT. Right. Okay, and I think that's what can be canceled. We are supposed to compare this with determinant of A times determinant of B. So let's do that. Determinant of A is AD minus BC. Determinant of B is RU minus ST. So once again, there's nothing we can do but to expand ADRU minus ADST minus BCRU plus BCST. Okay, and now we want to claim that this expression is equal to the expression for determinant of AB. So we have to match the terms. ARDU here is ADRU here. Good. BTCS here is BCST there. Okay, and ASDT here is ADST here. And finally, BUCR is BCRU here. So all the four terms match with the correct sign. So determinant of AB is determinant of A times determinant of B in the 2x2 case. So, and this gives you at least some confidence that this is true. In general, it's going to be a tedious proof, so we will not do it, but we will just quote it here. Okay, so that's first theorem. Now, second theorem. Again, A is an M by M matrix. And you have the A transpose. It's also M by N. The claim is that the determinant of A transpose is the same as determinant of A. Okay. Okay, so how do we prove this? So prove this, we can actually prove. The key point is that transposition exchanges columns and rows, right? So let, for the sake of notations, let MRS and NRS be minor matrices for what? I don't know, for A and A minus, I guess. For A and A transpose, respectively. Okay, then you just check that if you look at the ij's minor, this is the ij's minor for A transpose. That's the ji's minor of A transpose. Right, you check this, it's a fairly straightforward thing to check. Okay. Now, so now we proceed by induction. We want to prove that the determinant of A transpose is determinant of A. We prove by induction on the sides n. Okay. So when n is 2 being the first case, and being n equals to 2, in this case A is just A, B, C, D. A transpose is A, D here, C, B. They obviously have the same determinant, both equal to AD minus BC. Okay. So now suppose statement is true for O K by K matrices, K less than N. Okay. Now for A being n by n matrix, let's say A has entries Aij, then we can have the following computations of the determinants we need. Let's compute the determinant of A by the first row expansion. Okay, so that is A11 that M11 minus A12 that M12, and so on down to minus 1, 1 plus n, A1n that M1n. Now, for the determinant of A transpose, right, we're gonna use the first column, okay, expansion. And now here's the point. When you do first column, Right, first of all, it's the first term is going to be A11 times that of N11. Right, we've called NRS the minor matrix for A transpose. Now the next term, we're moving along the first column of A transpose, but the first column of A transpose is the first row of A. So the next term is actually A12 that M12, N12, sorry, N21. Right, this is moving along this first column, so it's N21, and so on. Finally, we get to N plus 1, A1, and the determinant and N1. Okay. All right. So now the point is, now, and all these determinants that occur in the expansion, they are of the form, well, determinant of N I1, I guess. And I1, as we observe above, NI1 is the transpose of M1I. Okay. So by induction, because this minus of size m minus 1 by m minus 1, the transposition by induction hypothesis, the matrix and its transpose have the same determinant. Okay, so we have determinant of Ni1 equal to determinant of M1I. I go from 1 to N. So that is to say that this determinant is equal to that determinant. This determinant is equal to that determinant, and so on. This determinant is equal to that determinant. So in doing this, you see that the two expansions match term by term. So therefore, these two determinants are equal. Okay. Simple. All right. Now let's see here. Right. Now there's another theorem that we want to discuss. Suppose T equal to Tij, I guess, is an M by M upper triangular matrix. Actually, it doesn't really matter upper or lower, but let's say triangular matrix. Okay. Then the statement of the theorem is that the determinant of this T is the product of the entries on the diagonal, T11, T22, down to TNN. Okay. And the proof will prove the upper triangular case. Which is to say that Tij is 0 for every I bigger than j. Okay. the okay. Let's see why this is the case. Sorry, let's see why it's enough to prove the upper triangular case. Only if T is lower triangular, then T transpose is upper triangular, right? By the construction of transposition, and by the previous theorem, determinant of T transpose is the same as determinant of T. So if we can calculate the determinant of T transpose, we calculate the determinant of T in the lower triangular case. And if the upper triangular case is calculated correctly, you get the determinant to equal to the product of the entries on the diagonal, then that's the same thing as, that will be the same answer. Put it differently, the determinant of T is determinant of T transpose, which is the product of the little t's. Okay, so let's just prove the upper triangular case. So suppose T is upper triangular, in other words, T looks like these: T11, T22, T and N, 0 down here, other stuff up there. Okay, we're going to compute the determinant of T by the first column expansion. Okay, that gives us T11, determinant of the minor M11 minus whatever other things you have. So, sorry, the other terms are all 0 because in the first column, there's only one possibly non-zero term, that's T11. All these other terms below it are 0. So it really is just T11 times the determinant of this new matrix, determinant of this matrix. The matrix looks like this: T22, T33, down to T some stuff up here, 0 down here. And you now see what you want to do. You can again try to compute this determinant using the first column expansion. That will give you T22 times determinant of another matrix, 0 down here. And all the other terms, again, because you're computing along the first column, and there's only one non-zero, possibly non-zero entry on the first column, you only get one term in the first column expansion, like that. And then you end up having to compute the determinant of another matrix of this form, and not yet, namely upper triangular matrix. So you proceed in the same way by computing the determinant along the first column. And in doing that, you pop a diagonal entry T33. and get another determinant of a matrix of the same form. So if you keep doing this n times, you're gonna get, well, at some point you're gonna get to Tm minus 2, Tm minus 2, oops, not that, Tm minus 2, m minus 2, that Tm minus 1, Tm minus 1, Tnn, something 0. And then this is just T11, T2 to up to Tnn. Okay. So, not bad. Again, what this is telling you, what this theorem is telling you is that for a triangular matrix, the determinant is easy to compute. You take the diagonal entry and multiply them together. Okay, good. So let's see. So let's do a remark. Now, if A, which is an n by n matrix, is invertible, right? Then there exists A inverse such that A inverse A is the identity matrix. So determinant, so you have the following calculation you can make. Determinant of A inverse A is determinant of I, the identity I. On the other hand, determinant of a product is equal to determinant of A inverse times determinant of A. Okay. Now, identity matrix is certainly triangular, or in fact, it's diagonal, right? So the previous theorem tells you that the determinant of I is just the product of the diagonal entries, and all those diagonal entries are 1, so you get 1 here. So what is this telling us? It's saying that the determinant of A inverse times determinant of A is equal to 1. So determinant of A, first of all, determinant of A is not 0. And secondly, determinant of A inverse is just the inverse of the determinant of A. Okay. Now, what is this saying? As you remember, being invertible is the same as being non-singular. So we have the following implication: A being non-singular, i.e. invertible, implies determinant of A is not 0. Okay? Or in other words, determinant of A being 0 implies A is singular. right? This is the contrapositive statement. So this is already telling you something about our goal, right? Remember in the eigenvalue problem, recall that to find eigenvalues, we need a way, a criterion for non-singularity or singularity of a matrix, right? And what we've just determined here is that if your determinant is 0, then your matrix is singular. And to make this useful for our purpose, we need the converse. So that is going to be the following theorem. Stated as follows. So A, again, is an n by n matrix. Okay. Then A is singular if and only if determinant of A is 0. In other words, A is non-singular if and only if determinant of A is not 0. Okay, so this will be the useful criteria we look for singularity or non-singularity of a matrix. And let's first remark that we proved the 2 by 2 case. We've proved the 2 by 2 case already, right? Because if the matrix A is of the form A, B, C, D, then we have the following formula. Let B be what is it? A D A what is it? A minus C minus B. Let B be that, and AB then AB is equal to BA is equal to and AB is equal to what? AD minus BC 0 BC 0 AD minus BC, which is AD minus BC times identity, or in other words, the determinant of A times the identity. And you can check that this is also what BA is equal to. So what this is saying is that if determinant of A is 0, then A is not invertible. If determinant of A is not 0, then A is invertible with inverse equal to 1 over the determinant AD minus BC, D minus C minus BA. Right, so this is therefore proving that being invertible is equivalent to being having non-zero determinant. And we've seen already that being invertible is the same as being non-singular. Okay, so this is the 2x2 case, and we're gonna spend some time proving the n by n case in general, but that's next time.